very happy to have Junior here. Peña from MIT. He got his undergraduate degree from University of Southern California, then went to MIT, where he has been working with Joe Formaggio and the Project 8 experiment. And yeah, today he'll tell us about Project 8 and how it is a promising path towards solving an 18-year-old problem.
Okay, happy to be here. And yeah, so I'll be telling you all about Project 8. The talk has two parts. First, I'll introduce neutrinos and neutrino mass, and then we'll really focus in on Project 8 after that. So we start by noting that neutrinos in the standard model are massless. But of course, in 2015, the Nobel Prize in Physics was awarded for the discovery of neutrino oscillations, which shows that neutrinos have mass. So the flavor eigenstates are related to the mass eigenstates via this PM&S mixing matrix. And so we know lepton flavor is mixed in weak interactions. So neutrinos can change flavor as they propagate. So if you go through the exercise of calculating the probability of flavor change in the propagation, you find crucially for this talk that it depends on the mass squared difference between the mass eigenstates. And so at this stage, many experiments have established this phenomenon, including Super K, Snow, and here I have a very famous plot from the CamLAN collaboration, clearly demonstrating this neutrino oscillation behavior. So at this stage, we know quite well these mass splittings between the eigenstates. We know that there are M1 and M2 are close together in mass, and there's a third eigenstate that's further away. But we, as of yet, do not know which of these mass eigenstates is the lightest, or what the ordering here is. So in the case where M1 is the lightest mass eigenstate, we call this the normal hierarchy. And in the reverse scenario, we call this the inverted hierarchy. So we know that these relative mass differences, but we don't know the overall scale here. So as it turns out from direct neutrino mass measurements, these lightest eigenstates are consistent with 0 and can range all the way up to 0.1 eV. So of course, this is a number that, so we know that neutrinos have mass, and certain people are just interested in measuring the number, but of course there's real physics reasons to probe the mass scale. The first one I want to talk about here comes from cosmology. So a second after the Big Bang, neutrinos decoupled from the cosmic plasma, forming the so-called cosmic neutrino background. And so as the universe expanded and cooled, the neutrinos transitioned from an ultra-relativistic regime where they served as radiation pressure, preventing gravitational clumping. They transitioned to a non-relativistic regime, aiding in large-scale structure formation. So there's a cool little animation of simulated universe in a box, showing how these large-scale structures form over time. At this stage, there's many cosmological measurements that give us information about neutrinos. For neutrino mass, the cosmologists fit this so-called matter power spectrum. And it turns out that, so the bottom plot is comparing this matter power spectrum relative to the massless neutrino case. And you can see that at different length scales, the neutrino mass can distort the shape of the spectrum here. And we'll come back to these kinds of measurements a little later. From the particle physics side of things, we know neutrino mass requires physics beyond the standard model. And the reason is we've only ever observed left-handed neutrinos. So we can't build these Yukawa couplings to the Higgs field as we do with the other standard model fermions without introducing a new degree of freedom to the standard model Lagrangian, like a heavy right-handed neutrino field. There's a range of questions associated with the mass scale, like how is the neutrino mass generated? Are neutrinos Majorana or Dirac? And of course, there's this large gap in the neutrino mass scale and the mass of the rest of the fermions. And so there's models that try to predict, for example, this gap. There's many different kinds of seesaw mechanisms to try to explain this. And there's also other theories that try to predict this fundamental particle spectrum from higher energy theories. And so really constraints that from data on the mass scale here would be really helpful in constraining some of these models. Okay, so whether you prefer cosmology or particle physics, hopefully now you're convinced that we need to do this measurement. And here I just want to focus on 3 ways that we probe the mass scale, starting with double beta decay. So there's this process that many experiments are searching for now, neutrinoless double beta decay, to nuclear decay, where that emits two betas and 2 neutrinos. If the neutrinos Majorana, they annihilate, and so you only see the 2 betas. It turns out that this the probability amplitude for this to occur depends on this M beta beta, so that particular combination of the mass eigenstates here. So this plot here is showing it's from the Corey collaboration, and it's showing this M beta beta parameter as a function of the lightest mass eigenstate. So again, if M3 is the lightest, we're in this blue-green band here, and the normal ordering is this purple band. Some caveats with these measurements are that there is a sizable theoretical uncertainty to the nuclear matrix elements for the various isotopes that are used, and that's still and that's quite challenging to get around. Moreover, if it turns out that neutrinos are Dirac, then this would be completely insensitive to the mass scale. Now on to cosmology. So as I mentioned, the limits are extracted from large scale structure data. The observable in this case is the sum of the mass eigenstates. And at present, the most stringent limits on the mass scale come from cosmology. Some issues here are that it is model dependent. So you can relax the limits by changing the model. And it also depends on the kinds of data you use and the analysis applied. More problematic though is, so this plot here is showing posterior distributions for fitting different kinds of data, this sum of the masses. And you can see that in all the cases here, the best fit value is in the negative sum of the masses, which is just unphysical. And at this stage, there's significant tension and growing tension with neutrino oscillations experiments. So that's these lines here. We know that there are lower bounds to what the sum of the masses is from oscillations. And so at this stage, these results are starting to rule out oscillations themselves. So from the neutrino mass side, this is interesting to observe. So this is definitely something to keep an eye on as we move forward with more data from cosmology and also from the neutrino mass side of things. So now we get to the central topic of this talk, probing the mass scale through beta decay. In this case, this effective neutrino mass parameter distorts the shape of beta decay spectra, as we'll see in the next slide. This class of experiment is usually referred to as direct measurements, and the reason is it's model independent. It's just a weak interaction, and the nuclear matrix elements, at least for tritium, are very well constrained. The problem, though, as we'll see in the remaining time here, is that this measurement is extremely challenging. So this plot here is showing this M beta parameter, again, as a function of the lightest mass eigenstate. You see the 2 allowed regions here. The world's best limit comes from the Catron experiment from last year, and they are nearing the end, approaching their systematics limited result, which is the dashed line, and as a preview, you see where project 8 comes in. Okay, so now more details on this high precision beta spectroscopy for the mass scale. On the top left is a tritium beta decay spectrum. So in an experiment, you have your tritium and the decay products, you get your helium, neutrinos that escape undetected, and we measure the energies of the electrons. The relevant factors of this electron energy distribution are given here, where you can see that when the electron energy is near this E0, the endpoint of the spectrum, which is effectively the mass difference between the initial and final state nuclei, that's where you get a maximal effect due to this effective neutrino mass. So if we zoom into that endpoint region, you can see that compared to the green, the massless scenario, when you have this effective neutrino mass shifts the endpoint and also distorts the shape of the spectrum here at the endpoint. So that's the name of the game. Measure electron energies as precisely as you can at the endpoint, and then you can perform this neutrino mass estimation. So this idea dates back to the 1930s. Fermi, this is from his the seminal neutrino, nuclear beta decay theory paper. So you can see his schematic of how the spectrum changes depending on the neutrino mass. The first measurement came a little over a decade later in late 1940s. That's these orange dots here on this spot. And we've been making steady progress to what we now know is the lower bounds on this effective neutrino mass. So as the title of the talk says, this is 80 years of experiments here, bringing us to current day, 2025, which was the last result from Catron. So here's Catron. They give a neutrino mass limit of 450 millielectron volts. And so here's how it works. On the left, you have your tritium source where your decays are happening. And so the electrons are being guided adiabatically, so without perturbing their energy through to this main spectrometer. And Catron is really an energy high pass filter. So they apply a potential such that only electrons above with enough energy can pass this barrier and make it through to their segmented detector at the end here. So you can see they vary this potential above the endpoint to collect data slowly. They scan through the endpoint region of the spectrum, and that's what they fit in the end to get the neutrino mass limit. So as I said, Catron is reaching its ultimate sensitivity of 300 electron volts very soon. And at this stage, this MAC-E filter technology is reaching its limits in background systematics, and also it's infeasible at this stage to scale any further. Their spectrometer is already 10 meters in diameter. More important for any future experiments is also the issue that tritium occurs as a molecule. So when you have a molecule and a decay happens, the energy that would go into the electron neutrino system can go into exciting the vibrational and rotational states of the molecule. And that in the end results in some energy broadening at your endpoint, which in turn means that there's a fundamental limit that you can be sensitive to this effective neutrino mass of 100 millielectron volts if you use molecular tritium. So any new technique needs to demonstrate better scalability and also be compatible with atomic tritium to avoid this final state broadening issue. And that's where Project 8 comes in. So here's Project 8 at our fall collaboration meeting. And so the experiment aims to probe the neutrino mass with a sensitivity down to 40 millielectron volts. And if nature is nice to us, measure the absolute neutrinos mass scale, or at the very least exclude the inverted ordering. Okay, so that was a whirlwind introduction. Neutrino oscillations imply massive neutrinos. We care about it from the cosmology point of view and also for BSM physics. And then we take a look at specific neutrino mass measurements. Now we'll jump into Project 8. So Project 8 performs this measurement using cyclotron radiation emission spectroscopy. And so the idea was originally proposed by Ben Monreal and Joe Formaggio in 2009. And the idea is fairly straightforward. You apply a uniform magnetic field to your decaying isotope of interest. And so when an electron is emitted, it undergoes cyclotron motion and radiating at the same time. So if you measure this radiation, it turns out that the cyclotron frequency is inversely related to the electron's energy. For concreteness, an electron with 18.6 keV energy, which is approximately the tritium endpoint energy, in a 1 Tesla magnetic field that corresponds to 27 gigahertz cyclotron frequency, and it radiates at about a femtowatt, which is quite low. So what makes CRES so nice for tritium beta spectroscopy? The first reason is that it's a frequency measurement. And as Arthur Shallow says, who co-invented the laser, never measure anything but frequency. In fact, we know that the highest precision test of the standard model comes from the electron G-2, which measures this constant out to 12 decimal places. And that, in fact, is a frequency measurement. The next advantage is that with CRES, you don't have to extract the electrons from the source because the tritium is transparent to microwave radiation. So we put that in contrast to the MAC-E filter case, where you have to transport electrons tens of meters without perturbing their energies or letting in backgrounds to a detector. In our case, our lives are much easier because we're just listening to radio waves. The fact that you don't have to extract these electrons then makes the experiment compatible with atomic tritium. So we also get to avoid this molecular final states broadening issue. CRES also allows for a differential spectrometer, which means that in contrast to Caltron, for example, where you have to scan for varying amounts of time through the endpoint of the spectrum to construct it, with CRES, you can see the full spectrum all at once. And these scans can take hundreds of hours. So that means we get increased statistical efficiency. And then lastly, CRES is very low background, so there's essentially no sources that mimic CRES electrons with the energy of interest. And really in previous experiments that have used CRES, the dominant background is just RF noise. And so lower background gives you better visibility at the endpoint here. Okay, so for all those reasons, CRES is very compelling. And so Project 8 is dedicated to developing this CRES technique in its path to probing the neutrino mass scale. And now we'll see a high-level overview of the development of the technology to that end. So in the early days, there was a lot of skepticism about whether CRES would even work. And so that was all laid to rest by 2015, the end of phase 1. And that was the first ever demonstration of CRES. That was followed up by phase 2, which, so here's the nice tritium spectrum that apparatus measured. This was the first CRES-based neutrino mass limit. We are now in phase 3, where we plan to demonstrate that CRES is scalable and that we have the technology to use atomic tritium. And the final goal of phase 3 really is to provide a Catron comparable neutrino mass limit. Then phase 4 is further scaling to eventually reach this target 40 millielectron volt neutrino mass sensitivity. So now we'll look at all of the phases in a little more detail here and slowly build up to that final sensitivity. Starting again with phase one, which was the first measurement of cyclotron radiation from a single electron. That was done using a waveguide that was terminated at one end and inserted into the bore of an NMR magnet. There was a gas supply feeding in krypton 83M, which is a metastable nuclear state. There's interaction with the atomic electrons, such that when the nucleus de-excites, it'll kick off the electrons from the orbitals. And so this source emits electrons at fixed energies, depending on what which orbital knocked an electron off of. And actually, you can see it here. So this was the krypton spectrum from phase one. So you can see the electrons from these various orbitals here. So the gas was contained in this cell here using RF transparent windows, where then the signal can propagate up through this waveguide to some amplifiers and then read out and digitized. So indeed, this is a very low power signal. And so it's buried in noise in the time domain. So we take a Fourier transform where we can pick out the dominant frequency component. And we can do this iteratively. So cut your whole time series up and perform the Fourier transform for each time slice along the way in order to construct these spectrograms. So we have frequency on the y-axis, time on the x, and out of the page is power. So what we're seeing, and this was actually the very first Project 8 event. What we're seeing is that at some point an electron is emitted and comes into view in the detector. It then emits this cyclotron radiation, losing energy in the process, and so it's rising in frequency. So that's what you see as these chirped tracks. And then on occasion, the electron will scatter off of the background gas in the cell, losing a lot of energy at once. And so that's what you see as these discontinuous jumps. Okay, now, so that was phase one. Phase two was used the same NMR magnet. There were some upgrades to the waveguide setup, but more importantly, there was this added infrastructure to support supplying tritium gas to the waveguide for an attempt at a neutrino mass measurement. So one thing I omitted in the last slide here is that there's a magnetic trap to hold the electrons in. So here's the reason why. It turns out that for sub-eV resolution with electrons in the field and energies we look at, we need to have about order kilohertz frequency resolution from signal processing or the uncertainty principle. For that level of frequency resolution, we need to observe these electrons for tens of microseconds. And it turns out that electrons we look at travel tens of meters in the amount of time that we need to observe them. So we trap them without perturbing their energy. And so we use a magnetic trap. There were two trapping configurations used in phase two. There's this shallow trap in blue. Then there's this deep trap in green here. And now notice that the cyclotron frequency we measure is a little more complicated. It depends on the energy of the electron, but it also now depends on the mean magnetic field it experienced while we were observing it. And so what happens is you can see in the shallow trap case where we're closer to that flat background field assumption, you have this really nice energy resolution. And then when we move to the deep trap for better statistics, because we don't correct for the field event by event, if you just assume a flat background field, that ends up broadening your energy resolution. And we'll come back to this in a moment. So this is the krypton 83 K line, which is used by these neutrino mass experiments because It's at 17.8-ish keV, which is very close to the 18.6 keV endpoint of the tritium spectrum. The nice thing about CRES is that we can shift the magnetic field in order to move the frequency of this line through the full range where we expect where the tritium beta decay spectrum is. And so that allows us to calibrate, to characterize the detection efficiency and the detector response at the tritium endpoint. So here's the result from phase 2. So importantly, this is indeed a very low background technique. There were no events observed beyond the endpoint of the spectrum in 82 days of data taking. And from the fit, you can see that there was a clear understanding of the detector response and a nice control of the systematics. The molecular tritium endpoint was in agreement with literature values. And so here are the neutrino mass limits that were obtained. So you might be looking at this and comparing them to the Catron results, and maybe you're not that impressed. But of course, phase 2, the spectrometer was just a very modest waveguide. And so we have a ways to go, but we believe we can do this with CRES. Okay. So that was phase 1 and phase 2. Now we look to the future, phase 3 and 4. We have this toy sensitivity model that looks at a differential endpoint spectrum with a window delta E at the endpoint. And we use it to inform our experimental design. So this is the uncertainty on neutrino mass, and there's 2 contributions. This left term here is the statistical uncertainty, and the right is systematic uncertainty. So we're going to work through it to see how eventually we get to the phase 4 sensitivity. Starting with this background contribution, moving forward, we need to keep that very low background that we saw in phase 2. And again, this is a contribution on the statistics side. There's also runtime, take more data, reduce your statistical uncertainty. And also there's this contribution of the uncertainties on the response function. And so going forward, we need to be as diligent in understanding the detector response and controlling the systematics. So this model was validated against phase 2 data. So you can see there the comparison with between the model and the data. And so we have some confidence that this can help guide our design moving forward. So there's also this effective volume factor here. And so we need to move to larger volumes to decrease this statistical uncertainty. And so here's the plan we have to move to larger volumes. We're moving from waveguides to cavities, and the reason is we can have orders of magnitude scaling in the volume, while also, because these electrons are exciting a resonant mode within the cavity, we have a resonant enhancement to the cyclotron emission. So that means improved signal to noise and higher detection efficiency. So we get a 2 for 1. The plan to move up with cavities is as follows. First, we're going to use this cavity CRES apparatus, which sits at about the same frequency as phase 2. It's mainly to demonstrate that we can do cavity CRES. And then we move to meter scale cavities with this so-called low frequency apparatus. So here's the start of phase 3, the cavity CRES apparatus, the CCA. So we have a copper cavity with a resonant mode at 26 gigahertz. It's surrounded by some electron trap coils produced here at Wright Lab by Talia. And we have an electron gun, which sends in electrons at fixed energies. Then there's also a gas line here that feeds in some gas. So electrons scatter off of the gas, and some fraction of those then scatter into our trap, exciting the cavity modes. We have a waveguide to extract the signal here, coupled through an aperture. So the signal propagates upward to a low noise amplifier and then read out and digitized. So CCA commissioning is underway. Here are a few pictures. You can see the trap coils, the cavity out separated from the trap coils, some of the team at the lab at the University of Washington doing some characterization measurements. We're moving up from that small NMR magnet. We now have a new to us MRI magnet. Here's the CCA inside. On the other side of the magnet is this electron gun. And here are pictures of some positioning of the electron gun. So at this stage, all of the prerequisite components for observing cavity CRES are in place. And at this stage, we are troubleshooting some of the components here, but we expect to see cavity CRES data very soon and officially welcome the phase 3 era with some data. So that's scaling volume. And now I want to switch over and talk a little bit about improving the energy resolution. I'll just talk about one component here. And that is going back to this magnetic field issue. So in phase 3 and phase 4, we want to have these deep traps for the statistics, but we also want to preserve this nice energy resolution intrinsic to CRES. And fortunately, there is a way to do this mean magnetic field correction event by event. So the electrons have this axial excursion in the trap. They are gyrating as well. That's just not shown in this animation here. So it turns out that the CRES signal is modulated by this axial motion in the trap. And so in the frequency domain, we have that central cyclotron frequency peak that we're already used to, but we also get these added features, sidebands, that are spaced at integer multiples of the axial frequency away from that central peak. So really the axial frequency is a proxy for how far up the trap walls the electron travels. So if we can reconstruct both the axial frequency and the cyclotron frequency, we have a way, we can use them both in conjunction to get a better determination of the electron energy. So here we are comparing the target CCA energy resolution to what was achieved in phase 2 for this pair of Krypton 83 N lines. And so the CCA will be the first experiment to resolve these two lines here, which are separated by only 0.7 EV. So along with being a proof of concept experiment that demonstrates cavity CRES for the first time, the CCA will also provide a nice physics result. Okay, that's energy resolution. And now this final factor I want to talk about is this N here, the source gas density. And really, I want to talk about the source gas itself. So coming back to what I mentioned earlier in the talk, we have this issue with molecular tritium where the final states brought in the energy resolution. And as I mentioned, CRES allows for a differential spectrometer. So using atomic tritium becomes viable now. And so the question is, you have this molecular tritium, how do you then produce an atomic tritium? And so there's a whole half of project 8 that's dedicated to solving this atomic tritium source problem. I don't have the time to give all the details here. I'll just lay out the general roadmap for how we think we can produce such a source. So we start with molecules and you have to break them apart. You can do that with heat or colliding electrons into the molecules using an electron cyclotron resonance plasma. once you have the atoms, you need to cool them down to temperatures compatible with trapping. And so the first stage of that is you can do two things. You can wiggle the beam about, and in these surface interactions with a cold surface, you dissipate some of the energy, or you can use a buffer gas. Then it turns out you need millikelvin level temperature, so you still need to keep cooling further, and also select the right states that you're gonna trap in the end. For the cooling side of things, we have planned to use this magnetic evaporative cooling, where as you're guiding the beam of atoms, you lower the magnetic potential so that the hotter atoms fall out of the trap. And in the end, you're left with atoms at the temperature that are required. There's also another source under consideration, this superfluid helium source, which is so it's a thin film of molecular tritium that you use an RF discharge electrons to crash into, and you get these atoms out at about 0.5 Kelvin. So this has been demonstrated with molecular hydrogen, and there are questions about whether it would work with tritium. So that's currently under investigation. In any case, once you have your cold atoms, you need to send them into your cavity and store them to perform the CRES measurement. And we do so using Yaffe magnetic trapping coils around the cavity. So I just want to spend a little bit more time on that last part, the trapping of the atomic tritium, because it poses a design constraint. So here are the Zeeman levels of tritium. On the y-axis is energy there. So you can see there are two states that minimize energy at low magnetic fields, and then two other states that energetically prefer large fields. So we know from Maxwell's equations that we can have static B field maxima. So we trap the low field seeking states. However, there's a slight problem that tritium-tritium interactions can cause these low field seeking states to flip into high field seeking states, which causes a loss mechanism for our trap. And you can see from this plot, so this is this dipolar loss rate as a function of magnetic field, and the dominant contribution here is minimized at low magnetic fields. So to reduce this spin flip loss rate mechanism, we need to move to low magnetic fields. And from the CRES perspective, this low magnetic field means low cyclotron frequency. But here's something nice. We wanted to scale the cavity volume anyway, and cavity volume scales inversely with frequency. So we were going to need low magnetic fields anyway. So here the two play nicely together. Okay, so after the CCA will come the low frequency apparatus, which is a meter length scale cavity. There will be an atomic beamline. Both will be tested with calibration sources, and will subsequently, there will be integration of the atomic tritium beamline. So this plot here is showing the limits on the neutrino mass as a function of experiment lifetime. In blue are our LFA scenarios, one more conservative than the other. Of note, though, is that the LFA will be the first experiment to use atomic tritium. And so after the LFA, there will be further scaling to another experiment, this red line here, where we plan to build a full-sized module for the neutrino mass measurement. And here we have we expect a neutrino mass limit of around 100 millielectron volts. And so when that full-size module is built, that will conclude phase 3. And phase 4 is then just iterating on that, building more of these modules to eventually reach the target sensitivity of 40 millielectron volts. So here's just a schematic of what such an experiment would look like. You have these meter scale cavities with your atomic tritium source. And with this, we believe we can reach that target sensitivity. So of course, this wouldn't be possible without all the lovely people that work on this experiment. Here's Project 8 at our collaboration meeting 2 weeks ago in Seattle. And of course, many thanks to the funding agencies that make this possible. With that, I'd like to conclude and see if there are any questions. Thank you.
So on slide 35, you made it very clear that we moved on onto cavities, but like, did we abandon the shallow trap and just keep the deep trap?
Yeah. Actually, our CCA traps look something like this. And I think going forward, we'll have this deep bathtub style of trap. Yeah, and the reason has to do with this axial frequency is deeply tied to the shape of the trap. And it turns out that harmonic shape is problematic for this axial frequency. So these traps makes it nice to work with.
Oh, sorry. Yeah, great talk. I was wondering what makes a good cavity for Project 8 beyond having a large volume? Like, do you have things that you care about for the mode shape or the quality or so on?
Yeah. So one factor is we need a low loaded Q. So we need these cavity modes. Actually, I think I might. So this comes from CCA cavity design. Essentially, we need these modes to be as broad as possible because the energy range of the tritium endpoints we want to analyze needs to be covered by the resonance bandwidth, basically. So that's one factor. We also need very large unloaded Q, and that's to reduce noise. Our noise model says that internal Q is a big factor. And then there's also, as you know, with the seamless cavities, we need to get electrons in using an electron gun. And so that's also a design constraint. Yeah.
Oh, yeah, it's very interesting. Very different from telescope cavities.
I was going to ask a naive question about the millikelvin for the atomic tritium source. Is that thermal noise, like thermal broadening of the line, or is it a recombination of the tritium or something else? Or?
I think it's required because otherwise it just it can evaporate over the edges. It's hot enough to
stay in the trap.
Yeah. It's just the potential barrier. Yes.
And a few more words about different cavities we might want to try in CCA.
Oh, right. Yeah. So the CCA is really a test bed. It's small enough and interchangeable enough that we can switch out parts. So there's ongoing designs for including more waveguides to look at more of the modes. And so that in turn can give you information about the electron's position in the cavity, depending on the mode shape. There's also another idea to cut the cavity in half and then build a polarized helium through to map the magnetic field inside the cavity. So yeah, there's many different things on the table right now, and that's also what makes the CCA nice, is that we can try these different ideas for the future phases where it's going to be a little more challenging when they're meter scales.
So you show the line of constraint on neutrino mass as a function of year. If I just blindly extrapolate that line, eventually I would reach 0 at 2060 or something. Is that what we should expect?
It depends who you ask, but yeah, so if you do this extraction, it's like 2050 for to the inverted ordering limit. Of course, we're ambitious and we think we can do better. But actually for probing a normal ordering, that's a hard problem. And so yeah, I don't know. It depends who you ask. You should ask around and see what bids you get.
Bits. Yeah, I mean, there is really no technology that we can think of right now that goes beyond this. So it's like, and even this is starting to stretch the limits of what you can do technically. The questions. If not, let's thank Julia again.